would mean that x3 would be constantly 0, right? That's what it would say, because we would not have this vector in the solution. Therefore, it would be only this vector times alpha 1. It would essentially say x3 is equal to 0 plus 0. So it would say that the optimal solution for x3 is 0. However, we see that the optimal solution for x3 is not 0. It is 1. Okay? So essentially, this final row this additional column was necessary, or is necessary, once you see a 0 in the corresponding row. Essentially, this null space always have to have at least one non-zero element in each row. Otherwise, you would lose information about one of the optimization variables. Okay? So that's why it is important to have all linearly independent vectors in here. Okay? And final thing is that this works wonderfully if the constraints are linear. Because all operations that we need to do, computing the particular solution and computing the null space, they can be easily done in MATLAB, in C, in whatever programming language. So the bottom line is, we can rather easily solve an optimization problem with linear equality constraints by eliminating those constraints and ending up with unconstrained optimization problem. Okay? So linear equality constraints are not a major complication. It's just one additional step and then applying your favorite optimization method to solve the unconstrained problem. Now, sometimes we also have nonlinear constraints. We have seen it in the box example, packaging box. The constraints were nonlinear. Those constraints cannot be automatically eliminated. They can be eliminated, but you have to do it manually from problem to a problem. Okay? So it's a manual job. Here we are talking about an automatic procedure which works always. Okay? So that's just to make you aware that the nonlinear equality constraints, they cannot be easily eliminated in general. Okay? There are particular examples where the elimination is easy. Sometimes the elimination is difficult. Sometimes it is impossible. However, sometimes, even if you see a nonlinear constraint, you can think about it and notice that it can in fact be converted to a linear constraint. Let me give you two examples. First one, x1 plus x2, and the whole squared is equal to 0. This is a nonlinear equality constraint. However, it can equivalently be also described by a linear constraint. Can you tell me which constraint equivalently describes this one? When is a square of something equal to 0? Of course, here we are only in real numbers, so no imaginary business. The term in the bracket.
The bracket has to be equal to 0, so
yeah, I mean
x1 is equal to minus x2.
Yeah, exactly. Yeah, precisely that. So we see that we had a nonlinear constraint. Thinking about it reveals that it is actually equivalent. Actually, this should go in both directions. Okay. Here, this is an equivalent linear constraint, and once we have a linear constraint, we can use the automatic elimination procedure. Okay? Here, it was not directly applicable. Okay? Let me give you a second example. Again, we are looking for a linear constraint which equivalently describes this nasty constraint. x1 is equal to 0, precisely. Yeah. There is no, I mean, this term here, I mean, it can be 0, but then the function would, or this constraint would be undefined, and for all other values of x2, this cannot be 0. Okay, so it all depends only on the value of x1. Okay. And I mean, these problems we really encounter in practice when you try to formulate a problem. You look at the physical properties, you look at the economics, and these nasty constraints, they kind of arise naturally. But then what distinguishes an optimization guy from somebody else is that the optimization person, he thinks about the problem. He tries to simplify the problem to obtain a problem which can be easily solved. Ideally, doing the simplifications in such a way that the problem remains equivalent to the original problem. Okay? And here, it's actually equivalent problem that we are solving. We are not losing any information. Okay? So I guess we can wrap it up here. So what we have seen was the elimination method for solving equality-constrained optimization problems. And in the next lecture, we will look at the Lagrange method, which has the advantages that here we can also relatively easily include nonlinear equality constraints, because we have seen that if the constraints are linear, not a big issue. We can solve the problem analytically, or using elimination and then using numerical methods, whatever. If the constraints are nonlinear, or if we do require something more to know about the solution, then we use the Lagrange method, as we will introduce in the next lecture. Okay. So that's it from my side. I would like to thank you very much for your attention, and if there are any questions, I will be happy to take them.